So, first calculus lesson. What are you guys going to be learning? What is calculus? It is the math of change or the math of infinities. We'll be dealing with infinities a lot. Infinitesimals, infinitely small, and infinitely large things. And there are really three major problems that was solved by calculus. We'll include a third one next to the first two. First one is finding the tangent line anywhere on a curve, or finding the instantaneous rate of change of a function. How quickly is a function changing at a specific spot, or how quickly is something changing at a specific moment in time? Essentially, it's the same thing. So in geometry, you can find, where tangent lines to circles are, but what if I just have a random function? How can I find the equation of that tangent line, and what does that mean? This is differential calculus. This will be the first third of class. Second problem is finding the area or the volume of an irregular shape. So we have area formulas in geometry for circles, rectangles, triangles, whatever. But what if I just give you some curve, and maybe I give you two places to start and end, and I say, what is the area underneath this curve contained between these two values? Calculus helps solve that problem. There's no geometric formula to find that. There's no, formula for the area of a circle, because that's not a circle. So in this situation, we'll be using calculus. This is integral calculus. We'll be doing that in the second third of class. The final thing that we will take on that calculus helps solve is, let's take just a sum of a bunch of things, like 1/2 plus 1/3 plus 1/4 plus 1/5, etc., 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 all the way out into infinity. So what if we sum up this infinite collection of terms? Well, I keep adding something that's smaller and smaller and smaller. Does that mean this will end up approaching or equaling a number, or is it going to keep growing? That's an interesting thing to think about, and the answer is interesting as well. This is when we get into series calculus, and we'll get there in the third third of class. Okay, but before we learn about any of those, derivatives, integrals, series, we need the building blocks of calculus, which are limits. Before we talk about limits, we're going to review function notation. Okay, very simple. Here I have a function given to you. We'll denote it by f of x. It is placed on top of an input axis. Typically, your input axis is going to be using whatever we are kind of the variable that is inside the parentheses of our function. Here is our function in terms of x's. So in this case, this is an x-axis. Sometimes you will have like f of t or v of t or something like that. Well, that means that input axis is now a t-axis. Doesn't always have to be an x-axis. Now what we have is our function values, which are graphed out. Okay, so for a given input, we will be graphing a function output. So this would be our output axis, and we call that our f of x axis. You're used to calling it a y-axis. It's not always y's, though. Sometimes we have velocities. Sometimes we have other things that we're looking at. Okay. Now, in this situation, if I give you a function value, an input value like 1, well, I can say my function value with that 1 being inputted, that will equal some value denoted by our graph. So if I look at the input value of 1 on the x-axis 1, the output, the point here, is at 2. So the function value at the input of 1 gives me the value of 2. That's why we say f of 1 is 2. If I go to an input value of 4, my function value at that input is 0. You can see the value outputted when the input is 4 is 0. Now we have a hole, so this function has a little bit of a blip here. This is telling me that when the input value of 3 is placed inside the function, there is no output value. We would say f of 3 is undefined. I'll use UND, short for undefined. There's no defined y value for the input value of 3 for this function f. Okay? However, that'll be just at the location of 3. I could probably go close to 3 at, say, 2.99, and I could probably guess that the y value, or the function value, that would be outputted if I use the input of 2.99, that would be close to -1. So maybe it's -0.99. All right, we can see there's a point right here, which is close to -1, and it's close to the input of 3. I could go to the right of it at, say, 3.001 and see that we're probably close to that value -1. But again, at 3, we don't have a function value. It's undefined. Okay? So, inputs and outputs. Sometimes we are given an expression with x's or some variable that will, determine what my output values are, and they'll follow some sort of trend. So if I say my function with x's is determined by the expression x squared plus 4x, well, you can just take a input value like 1 and evaluate f of 1 by taking wherever x is and replacing it with 1. And all of a sudden I find that f of 1 is equal to 5. And I can graphically see that if I look at a two-dimensional plot, x-axis, f of x-axis, the point 1, 5. Okay, and I can continue to do that for other values, either at whole numbers or at decimals, it doesn't matter. And what we will find is that when we plot all of the solutions, we would create a parabola that we are used to seeing. And the infinite collection of all the solutions creates this parabola. Okay, and I actually could have plugged any x value and I would have gotten a function value. Any x works. Well, let's look at the next one, this x squared minus 1 times over x minus 1. Well, if I plug in 0, I will get -1 over -1, which is 1. So I have the point 0.01, that's great. But watch what happens when I plug in 1. When I plug in 1, I'd end up with 0 over 0. You're not allowed to divide anything by 0, including 0. So this would be a situation where we have an undefined value. Now I could actually plug in values like 0.999 and 1.001, and I can find what that value is equal to. We'd be able to find those y values. I'd probably have to use a calculator to do that. But what we'll see is that at 1, I will have a hole, but around 1, I will have function values. And the function values will end up joining together to look like this. Okay. Then we have piecewise functions. Piecewise functions are made from expressions of whatever our variable is, in this case x, but we have constraints on our domain. So certain x's you want to use one of the pieces, for certain x's you want to use the other piece. Okay, in this case we are looking at to the left and to the right of 1. So when x is less than 1, I'm going to use x squared. So if I asked you what was h of 0, you would take 0 and square it and give me 0. If I asked you what was h of -1, you take -1 and square it, you get 1, giving me some points. But all other values approaching 1, getting close to 1, so like 0.5, 0.6, 0.7, 0.8, 0.9, 0.999, I could plug in and square it, and I would get function values out of it. So we would end up with these values that are getting really, really close to 1, but I would not have a closed circle using x squared at 1, 1. Instead, I can see that I'm going to be approaching 1 if I plugged in 0.9, 0.999, but I just leave that. And then if I look at the value at 1, well, the domain is defined because it's greater than or equal to 1 for 3x plus 1, so it's our second piece that will dictate what happens at 1. And I get 4, and then I keep going off from there using the 3x plus 1 piece. And from there. Okay, notice I have a closed circle using the 3x plus 1 because all the function values will get closer to this value, and then we include the 3x plus 1 at 1. But for x squared, we are leaving the x squared right at 1. So we're approaching a value, but we stop there. Okay, so that's piecewise functions. All right, well, now let's talk about the limits. Limit is the value that a function approaches as the input approaches some value. Okay? I can say, because I looked at 2.999 and 3.001, that my function values around this value of 3 is approaching this y value of -1. I can say my function is going to approach -1 as my inputs approach 3. Okay, I'm just going to write that down. Okay, but again, my function value at 3 is undefined. Okay, let's look at 1. Input of 1, my output is 2. I can also say, if I looked at 0.999 and 1.001, that my function values would be getting close to 2 as well. So I can say my function approaches 2 as my inputs approach 1, and I can also say that in this case, f of 1 equals 2. Okay? That is the concept of a limit. It's not what is going on at the location. It is what is going around a location. Not what is happening at that specific location. Okay, and we have notation for this concept of limits, okay? It goes as the following, just a random example. We'll use an undercase LIM. And then X arrow to some value. I'll denote some value as a C. And then we have a function that we're talking about, or we could have just some expression of x's. This could be like x squared plus 3x. You know, it could be anything. I don't want to confuse you, though, with that. And we say that is equal to some other value. This is read the limit as x approaches c of f of x equals L. This c is going to be a number. It's an x value. This L is going to be also a number. It'll be, you know, what you guys know as a y value. Okay, this x arrow c is as x approaches c. Okay. Now let's go back up here. Instead of this statement, I'm not going to erase it. I mean, you don't have to erase it on your paper, but I'm going to erase it here. I can do the same thing as I wrote down there, just using the limit notation. My function values, as we're getting close to 3, are approaching this y value of -1. I could say the limit as x approaches 3 of this function equals -1. Even though the function value does not exist, I'm not looking right at that location. It's almost like I'm excluding this location, excluding that circle. I'm just looking at my function values around, and I see my function values are approaching the y value of -1. Same thing here. In this case, my function value and my limits are agreeing with each other. I do have a function value at 1, 2. F of 1 is equal to 2. But also, my function values are approaching that. Okay, I would say the limit as x approaches 1 of f of x equals 2. What you can see is that in most places, for functions that are nice and smooth without any, holes, the limits and the function values typically agree with each other. Okay, but in this situation with our open circle, I don't have a function value, but I do have a limit. Okay, let's look at some other situations. Let's look at this other function, this g of x. It's a piecewise function. Now my question is, what is going on when x is approaching 1? Well, as I'm looking at 1, and I just kind of take out what's going on at 1 and I look what's going on around 1, well, it kind of depends on where I look at for what my values are approaching, okay? If I look for values just to the left of 1 at like 0.5 to 0.99999, my function values are down here at -3. But if I look to the right of 1 at 1.5 to 1.1 to 1.001, my function values are over here at this kind of this angled piece, okay, and it's approaching -2. So at 1, it's tough to say. It looks like we're approaching 2 different things, and we actually are. And because of that, we need the concept of a one-sided limit. We need to look not just at a specific area, but maybe to the left of the area and to the right of the area specifically. Okay, so what we have is left hand and right hand limits. I'll first give you the notation for a left hand limit. Limit as x approaches c, and in the exponent of that value, you'll put a little negative sign. And this means the limit as x approaches c from the left. It's called our left-hand limit, or LHL for short. And if you look on like the x-axis or on a number line, we'd be going from the left and approaching that value. So I use a little arrow to denote that I'm looking at my inputs, my x-axis, if you will, from the left, getting close to that value. Okay, we also have a right-hand limit. It is with a plus instead of a minus sign. So this is the limit as x approaches c from the right. It is our right-hand limit, or RHL for short. And again, if I looked at a number line or our x-axis and I have my input c, I'd be coming from the right, approaching that value there. Okay, so let's go back up. Let's not even worry about x approaching 1. Let's just look at a specific side of 1. Let's look at as x approaches 1 from the left of this g of x function. I would be approaching 1 from the left. So as I get really, really close to 1 from the left, where are my function values? Well, they're down here. And as I get closer and closer to 1 from the left, I'm approaching this y value of -3. I would say this left-hand limit of g at 1 is -3. If I looked at the right-hand limit, well, I'd be approaching 1 from the right. As I approach 1 from the right, my function values would be approaching this y value of -2. As I get closer to 1, I start on these values and get closer and closer to the y value of -2. So the left-hand limit is one thing, the right-hand limit is something else. Because the limits from both sides do not agree, we say the limit as x approaches 1 in general does not exist. We use DNE for does not exist. For a limit to exist, the left-hand limit must equal the right-hand limit. We don't care about the function value. We just care about the left-hand limit and the right-hand limit equaling each other. All right, IFF, if and only if the left-hand limit equals the right-hand limit. So let's go back to kind of our previous example with one extra little change, okay? We've looked at this before. We have an open circle around the location of 3, -1. But now I have a closed circle above it. What does that mean? Well, that means that my function is defined at 3, up here at 2. So I can go ahead and write 2 there. Okay? However, if I don't look at 3 and I look around 3, Coming from the left, approaching 3 from the left, my function values are approaching this open circle, which is at -1. If I'm coming from the right, my function values are again approaching this location at -1, which means my limit in general equals -1. It does exist. Okay? When the left-hand limit and the right-hand limit weren't the same, it didn't exist. We can look at a situation like at 1. Well, if I looked at f of 1, that's 2. If I look at the left-hand limit, that's also going to be 2. If I looked at the right-hand limit, that's also 2. The limit and the function value agree with each other. We are approaching 2 from the left, we're approaching 2 from the right, and our function values 2. So it's only in interesting cases like these with these open circles or that kind of jump that the limits sometimes don't exist, they don't agree with each other, and they don't agree with the function values, or the function values don't exist. Okay? All right. There's a lot of talking, but there's a lot of introduction. A lot of times we will introduce stuff and I'll be talking, but then I will set you guys free to do your own investigating, to discuss with your neighbors, to check with your neighbors, and make sure you are on track. Okay? We are going to be sitting in these locations for the majority of the class. Okay? And I will be asking you to work on certain problems and check your answers with neighbors, or to discuss a question that I've asked with your neighbors. It's a nice little collaborative process that we will be doing. Now, I don't want you to rely on one neighbor. I want you to utilize all of your neighbors. So I'd like you right now, and I know this is very uncomfortable for some of you. However, you're seniors. You can do it. Introduce yourself to everybody around you. And when I ask you to do these next 12 problems, I'd like you to check your work with everybody around you. I'd like you to feel comfortable saying, I'm not sure if I have this. Can you help me? And I'd like those of you who think they are comfortable with it to help others, okay? This is a collaborative class. We are going to help each other. We are not sitting in groups, but think of all of us as being one group of small little pockets of different groups, you know? Okay? So ready, set, introduce yourself to everybody. You're a senior, you can do it. And then after you've done that, do all these problems and see if you can get it, okay? Go. Introduce yourself to everybody around you, please. Mr. O'Keefe, do you know Mr. Wee? Okay, good, good. Ms. Noakes, do you know Mr. Wee to your left? Good, okay. Ms. Noakes is in my AB calculus class last year, so you can go to her for conceptual answers. And she's going to do her best not to just give you the answer. She's going to challenge you as well. Okay, now that we know everybody, here's a big graphical example. I want you to focus on the areas around -4, 1, and 6 for your inputs, and I'd like you to write down the answers to everything and check your answers with your neighbors that you know and just met. Once you're done, start checking your answers. Something to note is that function values are either defined or undefined. Okay, so we say this function value is defined, it's this, or the function value is undefined, UND for function values. Limits either exist or do not exist. So limits are either equal to a number, or we will use DNE for limits if they do not exist. Okay? I'm going to randomly call on people to give me the answers. So make sure you are on top of your game before I start calling on people.
No way.
All right, here we go. Randomly, using a random number generator, we have 21, Miss Hathaway. Give me your answers for the input value of -4. Undefined is correct. The open circle, there's no function value for that. Okay. What's next?
For the left-hand limit, I got 2.
Excellent.
For the right-hand limit, I got 2.
Yes.
So the limit is.
Correct. Very good. We're going to go with Mr. Pittman next. Mr. Pittman, for 1, what do you have?
I got 4.
4 is correct. The closed circle is up here, so that is the function value.
The limit on the left, 4.
Correct. From the left, we are up here at 4.
The limit
From the right is -2. So in general, it does not exist. Excellent. And then we will have Miss Drew. What do you have for 6?
I got 2.
2 is the function value. That's correct.
And then for the left hand, I got 5.
Yep.
And for the right hand, I got 5.
Yep.
And for the limit is 5.
Excellent. Okay. Now, we looked at these interesting locations, but I could give you an uninteresting location like at -3. If you took all these and I asked you what f of 3 was, what the left-hand limit at let's go to -3. -3 and -3, and if I change this to -3 and change this to -3, well, this location right here is boring because the function value exists, it's 3. The left-hand limit's 3, the right-hand limit's 3, and the function is 3, okay? So that's why we don't really pick on situations like that, because typically function values and limits are going to agree with each other, okay? So if I looked at this location, you would answer 3 everywhere, okay? Which brings us, and hopefully helps us with the next problem, is if I give you this situation, so this function f of x, and I ask you where do limits exist? So which x values will we have a limit? Let's see if you can get that. Go ahead and discuss that with your neighbor and see if you can get the answer. All right, Mr. O'Keefe, what do you think?
So limits would exist everywhere except for x equals -2.
Perfect. You can write that entire statement out, or you can just say for all x's except -2 and 2. That's the way we think about it. Limits typically exist everywhere. They equal the function values. It's only on interesting locations where that's not true. Let's just practice really quickly. Tell me the limit as x approaches -2 from the left and x approaches -2 from the right. Check that with your neighbor. Excellent. Excellent. All right, I think we have a solid understanding. This is -1 and this is 3. As I'm approaching -2 from the left, I'm down here. I'm approaching -2 from the right, I'm up here. Okay, so from the left, we're approaching -1. From the right, I'm approaching 3. All right, now there are some limit properties. A lot of properties in this class are very intuitive. However, properties in general in math are not necessarily intuitive. So that's why we will have some questions using properties. These will be fairly easy questions. You'll see them on your homework. I'll show you what would be the proper way to get the answer. First thing, if we have a limit as x approaches the value of a constant times a function, you can actually pull out that constant and multiply it by the limit of the function, if you know that. If you're trying to find the limit of two functions being multiplied by each other, you can just take the two individual limits and multiply those. Very intuitive. If I'm adding, if I'm dividing, it's the same thing. I'll need some more space for that. Oops. So you can add or subtract the limit of f of x to the limit of g of x. Same with dividing. Just take the two separate limits. Okay, we'll come back to these two. And let's go here to the next part, written functions. Typically, just like we talked about, limits and function values agree with each other. Okay? If I ask you the limit as x approaches a of f of x, it's typically f of a. Well, let's use g of x as x squared plus 3x. It's something we looked at before. If I ask you what is the limit as x approaches 1 of g of x, well, you know that x squared plus 3x, you know what it looks like. Okay, you don't have to graph it, but you know that it's going to be a parabola that opens up. There's no holes, there's no jumps, it's nice and smooth. You know that limits will exist everywhere and they will be equal to the function value. This is what this is saying. Typically, limits and function values are the same. So if you want to find the limit as x approaches 1 of g of x, you just need to find g of 1, which is 1 squared plus 3 times 1, which is 4. Now, I can kind of skip this whole, this is g of x, what's the limit as x approaches 1 of g of x? And I can say, what is the limit as x approaches 2 of 3x minus 5? Okay, I kind of just skipped it. I just said, that's my function. I plugged it into the limit. You should be able to get this answer. Because you know 3x minus 5, if I think of it as a function, it's a straight line. No jumps, no holes, no crazy things. The limit and the function value will equal each other. This limit will just be equal to 6 minus 5, which is 1. Does that make sense? Okay, so typically limits are easy. You don't even have to graph them to find the limit. You can just find the function value and assume that things are going to be nice and smooth around it. Okay, same thing for trig functions. If I ask you the limit as x approaches pi of the cosine of x, you know what the cosine graph looks like. Up and down, goes on forever and ever. There's no crazy jumps, there's no asymptotes, there's no silliness going on. All around it, the function values and the limits will equal each other. So if I ask you this, all you need to do is just find the cosine of pi. That's easy. Cosine of pi is -1. Okay? Well, what if I asked you what is the limit as x approaches a of c? Or, as an example, what is the limit as x approaches 2 of 3? Discuss that with your neighbors. What is that? Miss Van Dally, what do you think? Right, you can graph a function which is just equal to a constant. Okay, f of x can equal 3. Well, what is f of 2? Well, it's 3. What is f of -1? It's just 3. What does that look like graphically? A straight line through y equals 3. So no matter what your input is, whether it's 2 or whatever, your output is 3, and we'd be approaching 3. So the limit as x approaches a of c is just c, if c is a constant. What about the limit as x approaches a of x? What do you think, Mr. Minion? Well, if it was an x equals a equation, then yes, it would be a vertical line through a. However, x is not the same as x equals. We're thinking f of x or y equals x. What does that look like, Mr. Minion? Yeah, it's that diagonal line through the origin. What if I put 3 here instead of a? Who can help with that? Mr. Kobayashi?
One would be 3. X would approach a. The limit would just be a.
Yep. So since it's this diagonal line, the input and the output would be the same. This would be 3. If it was just a, we'd be approaching a. You just plug a into x. The limit and the function value agree. Okay? Let's go to this example. So this is using those limit properties. Okay, one of the properties we didn't really talk about that we'll be using here, but I'll show you the proper steps to finding the limit as x approaches 2 of f of negative x plus 3g of x. Well, you could essentially just start plugging in numbers and you get the right answer, but we should probably make sure by using our properties that we are going to get the correct answer. So what is the first property I'm going to use? I'm going to split up these into 2 because I know I have a plus sign, so I could just take the limits of this piece and then add the limit of this piece. So I'll have the limit as x approaches 2 of f of negative x plus the limit as x approaches 2 of 3g of x. Well, the other thing I could do, I know I can pull out this constant 3. I have that. Now, I have the limit as x approaches 2 of f of negative x. I don't see f of negative x anywhere. And I do see, excuse me, thank you, the limit as x approaches negative 2. Well, think about it. We talked about that typical situation. Typically, we can just take this 2 and plug it in and find the function value, right? So I'd have f of negative 2. Well, intuitively, wouldn't that be the same as the limit as x approaches negative 2 of f of positive x? Right? Because I would just be plugging in the negative 2 and I'd get the same thing. We can do that. All right, now I have things separated out and I can use these identities. We are told that this equals this and this equals that. I can say, okay, well, this is 6, I know that. And this is 3 times, limit as x approaches 2 of g of x is 8. So 6 plus 3 times 8 is 6 plus 24, which is 30. Okay. Now, sometimes it's not going to be that easy. Let's look at this x squared minus 1 over x minus 1. We looked at it in the past. If I asked you for the limit as x approaches 1, your first intuition should be, oh, let's plug in 1. Let's see what I get. So again, you can either ask this just like this is all in 1, or if you wanted to, you could say, okay, let's just denote this as a function g, and then let's say, what is the limit as x approaches 1 of g of x? Okay, these are, the same questions. So first attempt is to find g of 1. You plug in 1 squared minus 1, and then 1 minus 1, and you get that 0 over 0, which we know is undefined, which puts us in a tough spot. Lots of times when students run into this, since they see that the function value doesn't exist, they assume that this limit does not exist. But that is wrong. This limit actually exists. If we look at the graph of x squared minus 1 over x minus 1, we'd be able to see that. Now, it's not easy to graph that by hand. So let's use a calculator to help us out. Okay, so if you have a calculator, break it out. If you don't, grab one from the front. And I want you, using the graphing capabilities of your calculator, to find this limit. And make sure we're using parentheses when we're graphing x squared minus 1 over x minus 1. Don't think we typed it in correctly. Make sure that x minus 1 is in parentheses down there. Okay, so we can see the graph. There are going to be multiple ways for us to figure out what the limit is. Discuss with your neighbors the ways that you found, maybe. It's gone. Sorry. I have another one if you want. Graph looks like this, right? Looks just like a line coming out of that. That seems odd, right? So it looks like there's no problems. It looks like the function value and the limit should agree with each other. But what you should notice, and I like to use trace a lot in this class. I don't like to use the table. Table can help us, but I feel trace is a little bit more selective and powerful. Is that when you press trace, you can type in any value and it'll give us the function value. If I type in 1, I notice next to y there is nothing. Okay, but if I typed in 0, we get a value. If I typed in 2, we get a value, right? Well, that means what's going on is we have a situation where we have a hole. So we know that our function is going to be approaching the location of this hole from the left and the right, and that's going to be the limit. With our calculator, what is a way to figure out that location? Anybody raise your hand. What did you do? Mr. Gilmore.
You could put like 0.99 or 1.011.
It's a great idea. So why not just go really, really close to 1 instead of at 1? Why don't you type 0.999? And I see that y value is 1.999. If I try 1.0001, I see I'm really, really close to 2. Okay, that's one way. That's the way I prefer. You can kind of see that if you just kind of go to the left and the right, and you trace over the value. Anybody find another way to find that this limit is equal to 2? What did you do, Miss Driscoll, Lily?
If you look on the table, it's there.
Table is actually very, very nice to look at, and you can see that we go -2, -1, 0, 1, error, 3, 4. Well, you could probably guess where that location of that error is, right? It's right at 2. So that's good. However, I would not use the table. I would use trace and really, really close, like at 0.9999 and 1.001 to find that this is 2. Okay? Good. There are other techniques to find that limit. We are actually not going to worry about those techniques until much later in this class. So as long as you can use your calculator to find those limits and look at a graph and find limits, then you're going to be good to go. There is one other type of function, and a lot of times people get confused with piecewise functions and limits. But let's go ahead and tackle this one. So we have this function f of x. We have a domain restriction around 2, where 3 minus x is going to be used when x is less than 2, and x squared minus 6 is going to have all x's greater than or equal to 2. I have 2 questions. What is the limit as x approaches 2, and what is the limit as x approaches 4? Now, we'd want to do this without a calculator. Most of the stuff we do in this class will be without a calculator. But this first question, the limit as x approaches 2, is kind of a tricky one, right? Because we got one piece that gets left at 2 and gets picked up at 2. Okay, so sometimes it is helpful to graph by hand this piecewise function, or at least have a general idea of what's going on. So I'm going to do that. You do not have to graph these to get the right answers. You can kind of just figure it out. But let's see. So let's start to the left of 2. I'll be using 3 minus x. Plug in a couple values just to plot a couple points and understand that 3 minus x is going to look like a line. So I have 0, 3, 1, 2. And as I get close to 2, we are going to approach but not touch the y value of 1. So I get that. Now, at 2, we will be using x squared minus 6, so that'll be negative 2. And then I'll just kind of assume that we're going up from there. Well, this is showing us that the top piece and the bottom piece are not meeting up. So as I'm approaching 2 from the left and from the right, since I'm approaching 2 different y values, I can definitively say that this limit does not exist. But the left-hand limit and the right-hand limit can be found, so we should be able to find those one-handed limits. Oops. So go ahead and find the specific locations of the left-hand limit and the right-hand limit. And then find the limit as x approaches 4. Again, you don't have to graph to understand it, but it might help you. We could have just kind of plugged in 2 to the top piece, plugged in 2 to the bottom piece, realized they don't meet, the limit doesn't exist. Now, it's easy to see that as x approaches 4, we are just dealing with this quadratic piece, this parabola, and I'll be plugging in 4. 4 squared is 16. 16 minus 6 gives us the y value of 10. So that's what we get there. Okay? All right, that's all I got. Let's talk about your homework. Make sure everybody's on the same page for that. So today's homework is not a worksheet. Most of your homework is out of the book. Reminder, go onto the website, go to the assignment calendar. This is what is assigned. It will be due on Monday, okay? Most of it is out of the book. It's odds and evens because of just the problems that are asked. You go to this link to go to the online copy of the textbook, and then make sure you go to the correct chapter and section. Most of the problems are out of 1.2 and 1.4. And make sure you realize that you can click on an odd, and it'll give you the answers.
So we need to get go find a computer and sign on.
You need to make sure you get on Schoology. If you can't get on Schoology, just come ask me, and I'll give you the homework problems, and I'll give you a book if you need to. But let's get on Schoology.
Is there any login to get on the book?
No login to get into the book. It's just that link. Okay? Remember, the lessons page will have all of the lessons, videos of it. Come in if you have any questions.